y'all. We are doing 1.1 and 1.2 today, combining two things together. And we are looking at what I would consider to be the heart of Algebra 2. So what we're going to look at today is 4 different types of parent functions. But what Algebra 2 explores is pretty much every chapter is a new parent function. And we're going to do the same things with every single parent function. We're going to figure out what's the domain and range. How do we graph the parent function? How do we do transformations, which we're going to go over in today's lesson? And how do we solve equations with this parent function? How do we use this parent function to model real-world data or real-world phenomenon? So this is a really, really important lesson for us to understand the concept of. And fortunately today, it's really just the basics. It's learning the vocabulary of what is a parent function and how do I use these transformation rules. Okay, so I've been using the word parent function, and all functions belong to their own families. And just like families tend to look similar to each other, right? You and your siblings probably look similar, and your parents and your grandparents. That's the same vibe that functions are going to give, is that if they look the same, like if they're all horizontal lines, they belong to the family of constant functions. If they are all slanted lines, and they might be slanted with positive slope, or they may have negative slope, but those will all belong to the same family. They all belong to the linear family, or the family of lines. Okay? If they all look like V's, they all belong to the absolute value family. And if they all look like, kind of like U's, they're going to belong to the quadratic family. Okay, so that's what the families mean for functions. They all generally have the same shape. And then our parent function is really just the most basic function. And we can see down here we have the equations for my parent functions. And there's nothing extra going on in these functions. I'm not multiplying by anything. I'm not adding anything. The only one of these that really has a number, well, I guess there's 2. The constant function is just 1, right? Because it's equals a constant value. So the parent function is just going to be 1. The only other one with a number is our quadratic is x squared. And that squared is just giving the graph its shape. That's what squaring the x is what gives it that parabola shape. But other than that, there's no numbers with these. So the parent function's just the most basic. And then all of the transformed functions we can think of almost as like the children. They all are going to look a little bit different depending on what I add to them, or what I subtract, or what I multiply. And so we're going to talk about how do we know what that's going to make the function look like. Okay, so I went through and I already have the domain and range for all these functions, but it's a good chance for you to practice to make sure you know domain and range. And in example 1, it asks us to state the function family to which each graph belongs, and compare the function to its parent function. Okay, so again, we are going to decide the family based on what the graph looks like. So A looks like a V, so I can tell that belongs to the absolute value family. So I'm going to go ahead and put absolute value there. But we need to decide, how does this graph look different than the regular absolute value function, or that parent function? So I'm going to go ahead and graph in red what that parent function looks like on this graph. That's not in the directions, but it's helpful for comparing. Okay, so what I would describe, and we always describe how I would go from the parent, or from the red, to the transformed function. So I know we could say the parent function is down 1, but that is never how we want to describe it. We want to describe, I start with the parent function and I shift up 1 to get to the transformed, or the new function. Okay, so I'm going to go ahead and say it definitely goes up 1. Okay, but it also doesn't look quite as wide. It looks like I stretched it vertically. So we can imagine almost this being like rubber, like the red one's a rubber function. And if I grab the bottom and the top and I pull vertically, that's going to stretch it up to make it skinnier like this blue function. So I'm going to say it has a vertical stretch. Okay, and that's my goal with this section, is I'm going to name what family does it belong to and how is it different from the parent function. Okay, so B definitely is a line. Remember, we have two different types of line families. It can be a constant, but that's always going to be horizontal. And then linear is going to have some sort of interesting slope there. So I'm going to go ahead and say that this is linear. I'm going to graph that parent function. And you know what I didn't do on this last one? I did not label it. Y equals x. Y equals the absolute value of x. It's not necessary to do this, but it just points out that I was graphing the parent function there. Okay, and I bet you can look and see how this was changed, and there's actually two right answers. If you want to say that this function went up to, I think that is perfectly acceptable. But you could also say that this went left to, and neither one is more correct than the other one. They're both perfectly fine. You just can't say both of them, because if you did both, we would end up with a different line. But if you say either one, that is perfect. Okay, and C. C's definitely got that U shape, so I'm going to say that's part of my quadratic family there. Quadratic. And these four parent functions are the four parent functions that we're going to look at this first 9 weeks. Second 9 weeks, we will start to add different parent functions and just graphs that have a slightly different shape. We'll learn the name for them and we'll do all the same stuff all over again. Which is the great thing about Algebra 2, because once you get the hang of what we're doing here, you get to practice those same skills over and over and over again. So it's not like it's entirely new stuff every single chapter. We certainly do have new things, but you get into a nice routine, which is good. Okay, I would definitely say that this graph went to the right 3. And there's two different ways that we could describe what happens here. We can say that it has a vertical compression, which is what I would describe this as. Where, again, if we imagine that the red graph is rubber, and we take the top and the bottom and we smush the top and bottom together, we compress them, you're going to end up with this elongated shape here. So that's what's going to make that wider. Okay, but if it seems like I grabbed the left side and the right side of that red graph and I stretched them outward, moving it outward would be a horizontal stretch. And once we're doing algebra, we definitely will pick one of these over the other. Like we're gonna know when there's numbers involved which one it is, but if we're just looking at the graph, either of those is perfectly fine. They mean the same thing visually. Okie dokie, so basic transformation rules, just talking about those changes that we made. Up 1, vertical stretch. Up 2 or left 2, right 3, vertical compression. Okay, putting vocabulary to that. Transformations are what change the size, the shape, the position, or the orientation. Is it an upward U or is it a downward facing U? Okay, translations are the ones that don't change the size of the graph, it just shifts the graph around. So I'm going to go ahead and highlight in blue all of my translations from example 1. So up 1 would be a translation, up 2 or left 2, because again, that's not what's changing the size, it's just changing the position of the function. Okay, and then in green, I'm going to go ahead and highlight the scales. So the scales are what actually change the size or direction of the graph. So this vertical stretch, or this vertical compression, or again a horizontal stretch, or if I had a reflection, if it flipped the graph over and changed the direction that it was going, we would consider that to be a scale or a reflection. Alrighty, so we're going to go ahead and either use your calculator or use Desmos to graph the parent function of the absolute value, right? So this is my absolute value parent function. Because there's nothing extra going on with him. It's just the absolute value of x, and all that absolute value does is give it its shape. So I'm going to go ahead and graph that. Notice I put arrows at the end because it goes on forever. Okay, and now I want to look at algebraically, what do these transformations mean? So how do I know, without having to graph or without having to use my calculator, what would happen when I add 2 on the inside of the absolute value here, right? So maybe I'm just going to highlight. So this is definitely going to change it somehow. So this is definitely a transformation. And I do want you to use your graphing calculator right now to figure out what direction this is going to move the graph. So again, either on your calculator or on Desmos, type this in, and you should see that it still looks like the absolute value function, but it's just going to move it to the left 2. Which is kind of interesting that adding something inside the absolute value moves it to the left. That kind of seems opposite, because plus I normally associate with going this direction. But okay, so adding 2 moves it to the left 2, which means this should be the opposite, right? Because if adding 2 moves it to the left, I'm going to guess subtracting 2 moves it to the right, but I don't know. Let's see. Take some time, pause this video, type it in your calculator. It's just good practice. And you do indeed see that subtracting 2 on the inside of the parentheses there is going to move the graph to the right 2. Okay, in D, we are multiplying by a 1/2 on the outside here. So if you graph that, and it might be easiest to make sure that you still have this absolute value parent function graphed maybe in y1. So if you leave like y1 equal to absolute value of x, and then you can make y2 each of these transformations. So that way it's easier to compare. So maybe make y2 equal to 1/2 the absolute value of x. We should see the graph looks like a vertical compression. There we go. So we have a vertical compression. And this is one where I said once we have numbers, I know it looks like it might also be a horizontal stretch, but we definitely want to call this one a vertical compression, and I'll talk more about that in a little bit. Alrighty, moving on to E. We're adding 2 again. Okay, and up here, adding 2 moved it to the left, but let's look at the difference of where that plus 2 is. This plus 2 is on the inside with x, and we know that the x-axis is the horizontal axis, right? So this is not inside with x. So maybe when it's on the inside, it goes left and right, but when it's on the outside, what other direction could it move? And if you type that in your calculator, you'll see that that moves it up 2. Which this one isn't. Remember how I was talking about that positive we normally associate with going to the right. So these two rules on B and C seem kind of backwards. But when it's outside, when I'm going up and down, I do normally associate positive with going up. So that definitely just seems normal. It's more intuitive. Okay, which means I can probably guess without my graphing calculator, if adding 2 on the outside moved it up, then subtracting 2 on the outside must move it down. And if we check that in our calculator, that is definitely what happens there. Okay, we got 2 more. We have a negative for the first time, so we have this negative on the outside. What is that going to do to my graph? So type that in your calculator, type it into Desmos. And we can see that vertical reflection for the first time. So we have a vertical reflection. Sorry about my dog barking. Okay, and H. We are multiplying by 2, which let's review back. We have multiplied in front of the absolute value before. And when I multiplied by a half, that made it shorter vertically. So, uh-oh. My dog jumped on me. Let's make it back to, I closed out of my chapter 0 notes. Here we go, we're back in business. Okay, so when I multiplied by a half, that made it shorter vertically. So maybe multiplying it by 2 is going to make it taller vertically. Maybe that's going to stretch it. And if you type that in your calculator, that is exactly what happens. And that is a vertical stretch. Awesome. So we are going to use these transformation rules in every single unit coming up. And you know what? I think I mistitled this actually. Hopefully it's fixed on your notes by now, but if it's not, I have this whole table titled Translations. And this first section is all translations. But remember, translations just change the position. They don't change the size. So these scales and reflections down here at the bottom, those aren't really translations. These are just general transformations. And I think that's what I meant to title this. So I'm going to fix that. It's not a huge deal. But this should be my list of transformations. And again, this is so important because we are going to do this in every single chapter for pretty much the whole year. We're going to talk about different families of functions and what they look like, and how I graph them based on these transformation rules. So this is going to be really important for you to practice and kind of become second nature. Okay, so now we can use these rules to describe what happens on these graphs below in example 3 without actually having to use our graphing calculators. I know that on A, because of this guy, what it looks like, right? That's the function family. It's going to look like a quadratic. And then this part that I've highlighted in blue is my transformation now. And that is going to shift the graph down 1, right? Because it's not inside parentheses with x. When it's inside the parentheses with x, that's what shifts it left or right. So if it's outside parentheses, that's what's going to move it up or down. Okay, so this is going to move the quadratic down 1. Okay, B, I just see a regular x there. So I know that that's going to make it look like a line. That tells me my function family. And then this multiplying it by 3, that's my transformation. So that's going to be linear. With a vertical stretch. Okay, so identifying that function family, we see those absolute value bars there. So I know that this is going to be a V shape, right? Because that's my family. And this one has 2 transformations with it. We're multiplying by 1/3, so that's going to be a vertical compression. And then subtracting 5. And remember, subtracting 5 could mean 2 things. It could mean I move to the right 5, or it can mean I move down 5. It just depends on where it is. So we need to be careful. Remember, if it's inside with the x, x is my horizontal axis, so it's going to move it horizontally. So this minus 5 means it is going to move to the right 5. Okay, so this is going to be absolute value. I'm going to abbreviate that, abs value. And it's going to be, it's going to move right 5, absolute value right 5, with a, and since this is a number less than 1/3, that's going to be a vertical compression. And our very last problem. Woo! Okay, I see an x, I see a squared. That tells me what it looks like. It belongs to the quadratic family. Okay, and I can see 2 transformations here. The transformations are +1 and multiply by a negative. So remember, +1 could mean left 1 or up 1. Depends on where it is. Since it's inside with the x, that means my quadratic is going to move left 1 because it's inside with the x, and x is my horizontal. So quadratic goes left 1, and multiplying by a negative, that is going to be a vertical reflection. So with a vertical reflection. Beautiful. So that is 1.1 and 1.2 all together in one. And I will see y'all in the next video.